Okay, class. How are you? Okay, class. Today I will continue on the floating body. Alright. For this part, we're going to calculate the volume of submerged body. Remember our previous lessons, we learned about the buoyancy of submerged and floating body. Alright. The previous class, we only learned the submerged part. That means the body is totally submerged in the water. So to calculate the buoyancy force, which is mass acting upward vertically, it is gamma multiplied with the displaced volume. So what is gamma? Gamma is the gamma of the liquid that is being displaced, not the gamma or the specific weight of the body. Alright. So, and today we continue about the floating body. Okay, that means some part of the body exposed to the atmosphere and the other side in the water. Okay, so let's continue for this one. Okay, we finish this one. The buoyancy force FB passes through the center of volume of the displaced body. Okay, so center of buoyancy level will be B or CB. Okay, for example, this is body and this is the center of gravity or centroid. The buoyancy force must be act at the centroid. Okay, this is FP. So, when the body is submerged in the different fluid layer, some of the weight of each fluid layer displaced by the immersed body. For example, this layer, okay, filled with liquid A. And this layer filled with liquid B. And this layer filled with liquid C. And finally, this layer filled with liquid D. So, how many liquid we have? 4 types of liquid. Alright. So, to calculate the buoyancy force, it should be FB, buoyancy force, which is the summation of gamma I, V, I. For example, this is liquid A, liquid B, liquid C, and liquid D. Different kind of property. So to calculate that, which is gamma of A, displaced volume of A. That means only this portion. Okay. Plus gamma of B displaced volume of B, which is this portion. Alright. And so on. Gamma C displaced volume at C plus gamma D displaced volume at D. This is how to calculate the buoyancy force. Alright. So the floating body, consider the body in a liquid with a free surface. Okay. For example, we have a body and then this is at the free surface. That means some part of the body, okay, exposed to the air or atmosphere. Alright. This is water. And then let's label this is point A, point B, point H, and point K. At this body, will have the centroid, will act as the weight as well as the buoyancy. Okay, this is Fz prime. So let's say this is gamma of fluid. So from here, the Fb point upward must be equal to Fz prime. Okay, so again, the W here, the weight of the body, okay, the weight of this must be equal to buoyancy force. Okay, so what is the buoyancy force? Which is Fb equal to gamma of fluid multiply with volume, displaced volume. This is displaced volume. For example, I give you one example. We have this weight. The weight of this stone. Okay, this is stone. For example, this stone. Okay. So the weight of the stone must be equal to buoyancy force. So buoyancy force is gamma of the fluid multiply with displaced volume. Where is the displaced volume? This portion only. Only this portion considered as a displaced volume. So this one I highlight as a V displaced. Okay. So substitute in this equation, you will get the weight of the stone. Alright. So for example, a crane is used to lower weight into the sea. This is the sea level, alright, at the density given. For an underwater project, find the tension in the rope used by the crane due to a rectangular concrete, density 2300, block with dimension given. Alright, the first one, we must understand the situation. Alright, the first situation, it is suspended in the air. That means there is no buoyancy force acting at the concrete block. Only the weight and the tension. So this one, let's label FFT and this one label FW. So to calculate this, we must use the summation of force in y direction equal to 0. So positive outward, so Ft refer to the tension minus the weight of the block equal to 0. So Ft equal to weight. So to calculate the weight is rho g v. Okay, this is a volume of the block. The density is the density of the the density of the concrete rectangular. So it is given the density is 2300. Multiply with gravity 9.81. Multiply with the volume of the block. So what's the volume? This value. 0.4, 0.4, 0.3. And then you will get the final answer is 1083.02 Newton. Okay, that is considered for the suspended in the air for case A. For the case B, fully immersed in the water, that means 100%. So, again, we do the summation of force in y direction equal to 0. This case, yeah, case B. So, we can see we have three force components. The first one is Ft, and the second one, the wake, and finally, we have the buoyancy force, Fb. So, pointing upward positive. So Ft plus Fb because it is pointing upward minus W equal to 0. Thus to calculate the Ft, which is the wake minus Fb. So the wake we have calculated before. Alright. This is the wake. Okay. Because Ft is equal to the wake. We can directly substitute here. Minus with FB. Remember FB, the formula is rho G V. V is a displaced volume. So, 1083.02 minus the rho of water. This value. Okay, the rho of the sea water is 1025, gravity 9.81. And then the displaced volume is 100%, which is 0.4, 0.4, and 0.3 meter. So end up you will get the value of the Ft to be 600.368 Newton. Alright, that is the final value. Okay. This is example 4 is your homework. Okay, this is quite easy.
Sorry, doctor.
Yes?
I think got someone cannot see the screen. Doctor Sherry.
Okay, it is not moving.
I think he cannot see in the WhatsApp group. He say he cannot see the screen, Doctor Sherry.
Everyone, can you see the screen? Or is it some of you? Hello? Can you see the screen, class?
Boleh, Doctor.
Okay, okay. Okay, that is a bug lah, sorry. Okay, let's proceed to the next one. Okay, this example 5 is also your homework. Okay. Okay, I want to show you example 6. Okay. Example 6. The uniform 5-meter long round wooden rod is tied to the bottom by a string. Determine tension in the string. And B. Hello, can you hear me?
Can, Doctor.
Yes, Doctor. Can.
Yes, doctor.
Wait, yeah. Hello? Okay. Okay. Technical issue. Okay. Am I sounds audible for you? Everyone, just to check. Class, am I sounds audible?
Okay.
Yes, yeah?
Yes, doctor.
Okay. Thank you. All right. The uniform 5-meter long road. Okay, I have explained this one lah. Okay. The first part, when we look at this, the first we need to understand the situation. Okay, we have the long road. The size is 5 meter, only 4 meter submerged in the water, and 1 meter exposed. And the diameter is 8 centimeter. So we must convert into SI unit, which is 0.08 meter. And we have the water at 20 degrees Celsius. And then we have the string. The string will act as the tension. All right. So when we look at here, first we must draw the free body diagram to represent all the forces component. So I draw here. All right. And only this portion is 1 meter. Okay. What do you think the force involved? Definitely we have the buoyancy force. The buoyancy force must act at the centroid of submerged body. Where is the submerged body? From here to here. Where is the centroid? The centroid, definitely it is 2 meter, right? So this is the wake. Sorry, this is the buoyancy force. Okay. FB. Okay. And then what kind of
Sorry, doctor. Do you share screen for this?
wait, yeah.
Yeah. You did share screen, doctor. We can see.
Okay. You can see the screen, right? Can you try to sign out and sign in again?
Okay, sure. I try.
Because your friend can view the screen.
Doctor, I now cannot see the screen.
Or you cannot see the screen.
Just now cannot already.
Oh, no, cannot. Maybe internet connection. I try to use my own internet. Wait, yeah. Okay. Can you see now, class? The screen? Hello, please
Yes,
respond quickly.
Cannot see.
Can you see now, Tan BG?
Cannot. No.
Cannot, yeah. Anyone?
I can.
I can see. Boleh, doctor.
Cannot see also, doctor.
Okay, wait.
After I rejoin, I can see.
I can.
Okay, I try to share again. Can you see? Can you see, class?
Can.
Okay. All right. So we need to draw the free body diagram. I draw here. Okay, you can see we have the force. Okay, let's use the different color. This is FB. So what force involved? Other force involved. We have buoyancy, and then one more we have the weight. Okay, the weight of the rod. So where's the location of the weight? It must be at the central of what?
I meter.
Perfect. Central of 5 meter. Okay. So we have the weight. Okay. And then this is the weight, let's say. And one more thing, we must have the tension, which is here. Okay, the tension downward here to pull the rod. All right. So from here, how to solve this? Okay, first we need to find the tension. Okay, the question one asks tension in the string. We need to find the T. How to get the T? We can use the summation of force in y direction equal to 0. Okay, so the summation of force in y direction equal to 0, upward positive. And then you can try to solve this. You will get, okay, the positive one should be the FB. And then minus W minus T equal to 0. Rearrange T to be the subject. You will get FB minus W. So how to calculate the buoyancy force? The buoyancy force is very simple, which is, okay, FV equal to gamma. Okay, this is given or not gamma? Okay, wait ya. Okay, gamma and displaced volume. Alright. So what is the gamma of the water? Okay, the gamma of water is the standard one, 9790. You can use also 9810. It's okay, no problem. Don't worry. Okay, you have two choices. You can use 9810, 9790. It is almost close. Alright. And then multiply with the displaced volume. The displaced of the road. Where is the displaced one? Is it 5 meter or 4 meter displaced?
4 meter.
4 meter. Okay, so this is the cylinder. The shape of the road is cylinder. So we use the volume cylinder pi r, which is radius is 0.08 divide with 2 squared multiply with the height, which is 4 meter. You will get the answer, the buoyancy force, to be 196.84 Newton. So, you can substitute in this value here. How to calculate the wake? The wake of the road. Any idea how to calculate the wake? Okay. What is the formula for the wake of the road? Wake of the road is rho g v. The rho is the density of the road. It is not given. The gravity we know, the volume we know. Okay, the volume of the road is multiply with total Total length 5 meter. What about the density? Class, any idea how to calculate the density? Do you know how to get the density of the road? It is not the water density here, it is the road density. Okay, no idea. Alright. If we are not sure where to get the road, why don't we try another equation? Okay, this is for equation 1. Okay, we use summation of force. In order to get the W, simply we can use the summation of moment. Okay, we can use the summation of moment in counterclockwise to be positive moment at point T equal to 0. Where is the T? This T. Okay, because we want to eliminate T, we place the moment at T. If we want to eliminate the F, we can use the moment at F. Do you think we can use the moment at W? Class? Is it okay to use the summation of moment at W?
No.
Yes, but then we want to eliminate T, so put at T.
Okay. We want to eliminate T so that we can get W. If we put the moment at W, we eliminate W. So how to get W, right? So in order to get W, we must eliminate either FB or T. So now I want to eliminate T. So this will simplify my calculation. Alright. So again, we must use the moment equal to force multiplied with radius. So the moment must be perpendicular. This is not perpendicular. You can see we have the angle theta. So how to solve this? Okay, we must make sure we get into x. One. Okay, is it hang? Yeah. Okay. So I want to separate W in x component. Sorry, I think there is the internet very slow here. Okay, so this is W, X, and this is FB, X. Okay, so how to calculate the WX? By considering the theta here. Where is the theta? Okay, let me let me put this way. This theta refer to this theta. This theta refer to this theta. Okay. Okay, this theta refer to this theta refer to this. Alright. So from here, in order to get Wx, which is very simple. Wx is, okay. Yeah.
Doctor,
Okay, class. Sorry for the interruption because of the internet slow. Let's proceed. So, I want to calculate the moment for Wx. So this distance from this to this is how long? From here to here, how long? Any guess? Class?
0.5.
From here to here. 2.5. Right, because this is half. Is 5 meter. So half of it is 2.5. So Wx, okay, Wx multiply with 2.5. Okay, and then this is positive, yeah. You can use your hands. Okay, from here, use your hand from T, go here, and go to Wx. It is anti-clockwise. All right, so it is positive. For the FB, it is negative. You can see from T, go to FB and then follow the FBX. So it is negative. So minus FBX, okay, by considering this is X, this is Y, yeah, direction. So this is also cos, sorry, 2.4, okay, wait, yeah, minus FB, the distance is 2 meter. Okay, equal to 0. This is FBX. So, we know that Wx refer to the weight multiply with cos theta. Multiply with 2.5 minus FB cos theta multiply with 2 equal to 0. So cos theta cancel out, you will get directly W. W of the root, which is FB multiply with, okay, 2 over 2.5. So, what is the value of FB? FB we discover it is 196.84 multiply with 2 over 2.5. So, the weight of the rod, basically, let me use my calculator. 196.84 multiply with 2 divide with 2.5. It is 157.472 Newton. So we can directly substitute in this equation. We can find the tension equal to FB, which is 196.84 minus with the weight 157.472 Newton. And finally, our answer shall be 39.38 Newton. Okay, so that is the tension. However, how to find the specific gravity of the wood, which is gamma of the wood? The gamma of the wood we can directly get from the weight of the wood multiply with gamma of the wood multiply with volume of the wood. So, this is A. To calculate the P, we use the weight of the wood minus with gamma of the wood. Okay. Okay, this is specific gravity, sorry. Specific gravity basically of the wood is a gamma of the wood divide with gamma of water. Okay. So that means definitely we need to find the gamma of the wood first and then we can solve for the specific gravity. So, rearrange this equation. Okay, gamma of the wood equal to the weight of the wood divided with volume. So the weight of the wood or the rod is here 157.472 divide with the volume of the wood, which is pi r divide with 2 squared multiply with 5. Okay, the total length. So you will get here should be 0.082 squared multiply with pi multiply with 5. Okay, 157.472 divided with answer, you will get 6265.62. Okay. And then to calculate the specific gravity of the wood, which is gamma of the wood over gamma of water. So gamma of the wood is 6265.62 divide with gamma of water. Okay, this one 9790. Okay. You will get 0.64 answer. Okay, this is no unit. All right, so that is the final answer to get the specific gravity of the wood as well as the tension of the rod. Okay, any question so far? Okay, okay, let's proceed on the next part. The stability of completely submerged body. I give you the homework. Later on, I will share you the solution. Okay, 5, 4 and 5. Okay, so for this part, we need to investigate the stability of submerged body. Okay, for example, we have the body arbitrary shape. How to know whether it is stable or unstable? Right? The first we draw the arbitrary shape. For example, the shape like this. Okay, and then, all right, and then this shape, okay, have the center of gravity, which is this way. This is G. Of course, the weight should act at the center of gravity. And if this body, okay, have the centroid, maybe this is the centroid. I will explain later on the C and G. The centroid is where it is the volume centroid of submerged body. Okay, and then we have the buoyancy force, FP. Alright. So what happened is that this is unstable because it will cause a rotation. Okay, it will cause the rotation in, okay, in this direction, either in the clockwise direction or anti-clockwise direction. Because you can see this point is meeting to each other, G and C. Okay, FB meeting with W. It will cause the rotation. So definitely it will not stable at all. Okay. For the neutral, okay, this is the case for the neutral. That means it is balanced. Okay. Once you touch, it will move. This one, when you give a force, the small force, it will rotate. Okay. However, for the neutral one, okay, the C and G at the same point. This is C and this is G. So the weight here, this is the weight and this is the buoyancy force. Okay, this is stable. It will not rotate. It is fixed. Okay, because C and G at the same point. Center of gravity and the center of coincidence. Alright. However, for the stable one, you can see we have the body. Alright. We have the C here. And then we have the G here. Alright. The C refer to the buoyancy force, which always acting upward. The G refer to the weight. You can see when you have this kind of body, someone try to pull this way and someone to try to pull this way. What do you think? It will become stable. It will fix. No motion. Okay. Even though you try to give a rotation in this direction, due to the pulling force in opposite direction, it will remain stable. Okay, it will remain stable. It will retain back. That is what we call a stable. So, as the center of gravity is below the centroid, a small angular rotation provides restoring moment. Okay, this will provide the restoring moment that restore the original position. So, this is example of stable. Okay, you can see this is very stable. You try to move this way. Okay, it will retain to the original position. This is neutrally stable. It is initially stable, not moving. You give a force, it will move and stop here. However, for the unstable, initially it is at this location. You give small disturbance, it will move. Okay, unstable. Alright. After we know the object is stable or unstable because of the C and D, for example, we have the boat. Alright. We need to know the keyword here. The metacentric height, referred to GM, is the distance from G to the point of intersection of the buoyancy force before rotation, which is A. You can see this is A. And with the buoyancy force after rotation, which is B. Alright. Okay, this is, I highlight again, this is before rotation. This is after rotation. So basically, where to get the metacentric height? GM. Alright. The first one, the G always the same because the G is the centroid of the object. Whether it is submerged or unsubmerged in the water, the G will remain the same. For the C, it will depends on the displaced body, displaced fluid. Alright, this is the boat. And then we specify the gravity centroid G. This is G. And after rotation also, the G also the same. Nothing changed, yeah? The G always act at the same position. Alright. And then this is C. How to get C? C is a displaced volume centroid. So this is the water. This is water. That means the displaced should be here. So the displaced here, the displaced of the volume is here. So where is the centroid? The centroid at the center of this place. Okay, this is centroid. So we define the buoyancy force acting at the centroid and the weight of the object acting at the center of gravity, G. Alright, this is before. After we After the rotation, we give a small disturbance, it will rotate. Whether it is remain to the original position or it is restoring the movement or not. It depends on the GM. Let's see, after we try to rotate, this boat will be like this. Okay, the G always the same. However, the direction always vertically downward. Okay, this is G downward. Right. Okay. However, the line of action at G shall be the same. Okay, same goes here. However, if we try to rotate, the displaced volume will be different now. You can see this is water, this is displaced. Okay, so the displaced volume become like this. Do you think the C will be different or same as before? The C, the centroid position of the displaced volume, is it the same or different?
Different.
Yes, different because different displaced volume, right? This one is displaced like this and suddenly you try to rotate, it displays in this position, in this shape. Definitely the centroid of the displaced volume will be different. So let's say the centroid is here. We have the buoyancy force acting upward. Okay. And then the distance from G to M is, you can see the intersection. Before and after for the buoyancy force is this M. Now we introduce you the M. The distance from M to G we call a metacentric height. This one. This is GM. Okay, the distance here. So your job, basically you need to find the GM only. If the GM is positive, it is above the G, it is stable. If it is below the G, if M below the G, it is unstable. Okay, this is the boat. Alright, and this is this is the G, and this is the C. The C is upward. Sorry. The C, the force at C is the buoyancy force. FB. And this is wake. You can see it is pulling each other. You try to give the rotation in this way, it will restore the position. That is why this boat is stable. However, the boat will not stable if like this. Okay, if the G here and the C here. Okay, so you can see the G is acting downward and the C is acting upward. You can see it will rotate clockly. It will rotate when you give the disturbance. So this is unstable. This is stable. That's it. Very simple. Okay, how to calculate the GM? We have the formula. The GM value is GM equal to second moment of inertia over displaced volume minus CG. CG is the center of centroid displaced volume to the G. This one, yeah. This is CG. Right. So I give you one example, very simple one. A 0.25 meter diameter cylinder is 0.25 meter long, act composed of material with specific weight, gamma, 8,000. Will it float in water with the end horizontal? Okay, we have the cylinder. Okay. I draw like this. This is cylinder. Keep it. And then this is long. All right. And it is exposed in the, okay, it is exposed one at the top side. Okay, so the question asks, will it float? Will it float with the end horizontal? Okay, that means this is end horizontal. End to end, whether it is topple in this direction or topple in this direction. Very simple. Okay, so you want to test whether this is stable or not, topple in the end horizontal or not. Right? So from here, let's give the value. Okay. The submerged, okay, where is the G? The G, remember, is the center of object. Whether it is submerged or unsubmerged, it always the same. The G is, for example, this is from here to here is 0.25. So where is the G? 0.25 divide with 2. So the G will act here. This is G. Okay, the center of gravity for the object. And we must know the distance here and here is 0.25 and here as well 0.125. Okay. So, however, how about the C? Any idea how to get the C? The C shall be acting for the displaced volume. Where is the displaced volume? This is the displaced volume. Now, where is the C? Is it below the G or above the G?
Below.
Below, perfect. Okay, now we have the, sorry. Now we have the displaced. This is the displaced. We must refer to the displaced one. So the center of displaced volume shall be here. This is now become C. All right. So our equation, we need to find the GM, whether it is stable or not. So the GM equation should be, remember, the GM is second moment, okay, over with displaced volume minus with CG. All right. So we must know how to calculate the second moment. I naught, okay, the second moment of circular cross-sectional area. Okay, how to know the shape of this object? Okay, first we must know is it a float with the end horizontal? We must look at from the top. Okay, whether it is topple in this direction or in this direction. So what do you think of the shape when we look at from the top? It is It is circular cross-section view, right? So it is circular cross-sectional view. With the diameter given here is, okay, with the diameter to be 0.25 meter. So applying the second moment for this circular cross-sectional area, you can look at the table later on. I note for this shape, circular shape, it is pi d4 over 64. So pi diameter is 2.25, okay, 0.25, the power of 4 divide with 64, it is 0.000192 meter the power of 4. So now we discover the I naught. Okay, I naught we got. However, to find the V, displaced volume, this is the displaced one. How to calculate the displaced volume? Okay, the V displaced. What's the formula which is? Any idea how to calculate? So we can use, okay, the weight of the displaced water. Okay, weight of the displaced water equal to gamma of water multiply with displaced volume. Okay. Okay, wait ya. I want to show you very simple. Okay. We have this shape. How to calculate the weight? Refer to the buoyancy force, right? We have the buoyancy force. Remember? The buoyancy force acting at the C or G? Definitely at the C. This is FB. How about the weight? The weight almost act at the, should act at the G. We have the weight. So you can see the weight of this cylinder is equal to FB, right? Okay. So the weight is given or not? The weight of this cylinder. It is not given, but the given one is the gamma. Okay. The gamma of the cylinder is rho of cylinder, G and V. V of the cylinder equal to the buoyancy force. The buoyancy force is the, okay, rho of the water, gravity multiply with displaced volume. Displaced volume, this one. Alright, so G and G we can cancel out. So now we can get the V displaced equal to rho of the cylinder multiply with the volume of the cylinder divide with the density of the water. So the density of the cylinder, sorry. Okay. I think this is not the density. This is the gamma. Alright. So better not remove the G. We convert directly from here lah. Okay. Gamma rho multiply with G is a gamma C. Very simple one. Rho multiply with G is a gamma of water. Simple this one. Okay, this is displaced. So volume displaced is equal to gamma of C multiply with gamma of water divide with gamma of water multiply with volume. So gamma of cylinder, where is the gamma of cylinder? Yes, it is given. Material specific weight is 8,000. divide with the density of the gamma of the water, which is 9810. You can use 9790 also can be accepted, don't worry. Right, multiply with the volume of the cylinder, the total volume, yeah. So from here it is pi r, which is 0.25 squared multiply with the height, which is 0.25. Okay. Okay, I delete this one lah. Okay. So after I calculate here, I will get the V displaced shall be 0.01 meter cubic. Alright. After I discover the I naught, the V displaced, I need to find the CG. So how to calculate the distance from C to G? You can look at here. Okay. CG. I want to calculate the distance. CG. Okay. Let's analyze. I want to know this one only. The CG. How should I do? Any idea how to calculate the CG? We have all the dimension. Very simple. Any idea?
0.01
0 point. Which one?
divide
0
by
point. 0
volume
point.
displaced. Volume display over the pi r square.
Over pi r squared.
Because the volume display is pi r square over the length of under the water.
Okay.
So using the
Okay, yes, perfect. So we miss one thing. We need to find the depth, right? From here. Yes, correct. From here to here. After we know the depth, then we can solve for CG. Okay, we must know the depth because we are referring to the displaced volume. So how to calculate the depth, the D? Okay, by referring to the displaced volume, okay, we know that the depth is equal to displaced volume divided with the area. Okay, so this is the displaced equal to 0.01 divided with the area of this circular shape, which is pi. Okay, pi d squared over, sorry, pi squared over 4. Alright, this is the area of circular. You will get the depth to be 0.204 meter. So the depth here now to be 0.204 meter. Okay, so how to get the C? The C definitely the depth divide with 2, right? Okay, you can see to get the C, okay, from here, let's say from here, definitely the depth divide with 2. Right? And then we have the G here. Okay, the G 0.125 from here to the depth. So to calculate the C and G, C to G, which is 0.125 minus with this one, D over 2. Okay, so 0.125 minus with 0.204 divide with 2. You will get CG equal to 0.023 meter. So we have all the value. So substitute in this final equation. Alright, GM. GM equal to I naught, which is 0.000192 over with displaced volume, which is 0.01 minus with CG 0.023. Finally, you will get negative 0.004 meter. Okay, this negative, this is negative value. Okay, the cylinder will not float with an horizontal. Okay, that's it. That is the final answer. Okay, any question so far? Us? You can look at, you can view. Okay. Alright. Let's proceed on the linear accelerating container. Okay. So in this section, the fluid will be at rest. Why it is at rest? Okay, because we are referring to the relative reference frame that is linearly accelerating with the horizontal component AX and the vertical component AZ. Then the equation 236 simplify to this. Okay, let me tell you, this whole case is considered as the static. Okay, it is not moving. While in this mention, it is linearly accelerating container. We can see why it is accelerating, and when we solve, it is static, it is not moving. Alright, you can see these definitions. The fluid will be at rest, relative. The very important word, relative. Reference frame. That means when we solve it, we must have the reference frame. So even though this bucket, okay, keep moving to the right with the acceleration value. However, this liquid in the container is at rest. This one. We are referring to this one. We don't care about all this thing. We care about the fluid. Because our reference frame now is this bucket. This bucket here is our reference frame. That means our home. Okay. So let's say this is referred to, okay, this is Y and this is X. Okay, do you think this particle, okay, when we refer to this position, it is moving? For example, this one, even though the bucket is moving, what do you think of the particle? The fluid position. Is it different from the reference line, from the reference point? Class? Can you hear me? Okay. What do you think the particle in the fluid when referred to the relative reference frame? Is it at rest? Class?
Don't know.
It is not moved. It is still at rest. Okay, because our reference frame now is the bucket. That is why we consider as the static or rest relative. Okay. So, do you still remember the hydrostatic equation? So, what is our hydrostatic equation? The last class we learned about hydrostatic equation. P2 minus P1 equal to negative gamma of water Z2 minus Z1. Right. Okay. Following the book, when you study chapter 2 in the book, the hydrostatic equation basically derived in three components, X, Y, and Z direction. In this is only refer to one directional only. Okay. So for this part, one directional. For this part, it refer to three dimension. Okay, which is X, Y, and Z. That is why dP here basically the change of pressure at point A and point B equal to negative. You can see I have the negative as well. Okay, rho A. Rho A is basically the gamma because gamma is equal to rho G. G is the acceleration, gravitational acceleration. So, G refer to the A, Z lah. Okay. Sorry, it is refer to the gravity. So, rho A, like a rho G, is a gamma as well. Okay. Okay, gamma as well. Okay, this is gamma as well. But this one, since this fluid moving at the acceleration, we must plus AZ lah. Okay, because this is the external acceleration. The gravity is fixed. Okay, this is what you need to know lah. The equation of 236. The equation 236 basically derived from hydrostatic equation in three-dimensional. So, once we try to, okay, okay, so this with horizontal component and vertical component, okay, that means we are referring to two dimension only, okay, 2.2.3.6 is 3 dimension. This refer to 2D only. That means we involve in Z and X direction. This is our coordinate. Okay. So only motion AZ and AX motion. There is no Y motion. That means there is no motion into or out of the page. Okay, the motion into and out of the page is 0. We don't consider. So if we don't consider the motion into the page, okay, that means we can cancel Y direction equal to 0. Then the equation become this equation. So integrating this equation, you will end up like this. The same hydrostatic equation, P2 minus P1 negative rho AX, Z2 minus Z1. Okay, this is X2, refer to P2. This is X1, refer to P1. Very simple. Okay. And then for the gravity, negative rho, remember that the gravity must plus with the external acceleration, G plus AZ, Z2 minus Z1. Okay, this is after we do the integration. And then, if point 1, if pressure at point 1, okay, if the pressure, this pressure on the surface, and it is exposed to the atmosphere, we can consider that the P1 and P2 is the same. Okay. So we can cancel P1 minus P2 equal to 0. So we end up, we rearrange the equation, it will become Z1 minus Z2 over with X2 minus X1 equal to tangent alpha. This is in terms of the dimension. However, for this one, it is in terms of gravity. We have one equation, we have two equation. Okay, to simple the equation, to simple the case, to ease the case, all right. This is the coordinate, this is triangle with the alpha. Okay, the distance from here to here is Z1 minus Z2. Okay, because we have this point, this is point 1 and this is point 2. Definitely 1 minus 2 to get this distance, right? Okay, to get this distance from here to here, definitely x2 minus x1. Okay, this is x1, this is x2. So to get the tangent, alpha, tangent opposite over adjacent. So opposite is Z1 minus Z2 over with adjacent X2 minus X1. Okay, that is why you have this equation. Okay, tangent alpha equal to acceleration in X direction over G plus AZ. This is what you get after you rearrange this equation. You will end up this equation. Okay, let's take a look example this. Okay, this is the final one. The tank shown in figure E2.2 is accelerating to the right. That means this at A is initial and B is after acceleration. Calculate the acceleration AX needed to cause the free surface. That means the question asks find the AX that require to form like this. To form like this shape. Okay. To touch point A. That means this liquid container want to touch at point A. Okay, this end must touch this like this. Also find the PB and the total force acting on the bottom of the tank if tank is width 1 meter. Okay. To solve this question, let's list out our equation here. Okay, tangent. Okay, now we have Z2. Okay, let's place our equation. Z1 minus Z2. Okay, over with X2 minus X1 equal to tangent alpha equal to AX over G plus AZ. Okay. So the first step, we need to find, we can see we have the X here. Definitely we need to find the X component. Okay, so that, why we need to find the X component? Because we need to find the alpha here. The alpha, we can use tangent alpha equal to opposite over adjacent. We know already this distance, which is 1 meter plus 0.2, which is 1.2 meter. How about this distance, which is x? So we need to find the x first in order to get the alpha, tangent alpha. So this one, opposite is 1.2. Adjacent here is x. We need to find the x. So how to get the x? We can use the ratio, okay? We can use the ratio of initial and final, okay, of the area. Okay, the volume lah, the volume ratio. The volume, okay, for example, this is the volume. Okay, try to delete this one lah to make it easier. Okay, the volume of this air is the same as this volume. But the difference is the shape lah, okay. The volume of air before is like this. Okay, equal to the volume of air after, like this. Okay, the volume will not change. So how to get the volume? Okay, 0.2 multiply with the length 2 meter multiply with the depth, it is given the tank width is 1 meter equal to the volume of this, which is half triangle, yeah, triangle, right? And then the total length here is 1.2. 1.2 multiply with x. Multiply with 1 meter because it is the width. So we will get the x here to be 0.667 meter. Alright. So from here we can directly plug in the tangent. Okay, tangent alpha is equal to 1.2 divided with x, which is 0.667. You will get 1.8. That means the tangent alpha equal to 1.8. Alright. So from here the question asks, find the acceleration ax. Where is the ax? Okay. This is ax. The question want to ask how to get this one. We can use this equation. So tangent alpha equal to ax over g plus az. Okay, what do you think of the az? You can see the motion in the horizontal direction. Is there any motion in the vertical direction? Okay, this is x and this is z. Is there any motion in the vertical direction, class? Hello?
No.
No. What do you think of az?
0.
0. When there is no motion, az also 0. Clear? So no motion in z direction. We can cancel out az. Okay, because az is 0. No vertical motion. Alright, it's very clear. So directly you will get az, very simple, g tangent alpha. G is 9.81. Tangent alpha is 1.2. 1.8. You will get the final one to be 17.66 meter per second squared. That will cause this shape. Okay, like this. And finally, the question asks find FB. Find PB. The pressure at B. This pressure. This is pressure at B. This is pressure at A. So we have 2 points, A and B. So using our hydrostatic equation, you can use this one here. Okay, P2 minus P1 equal to negative rho. Okay, which direction motion? AX or AZ? Class? Definitely, it is
Yes.
AX only, right? There is no motion in vertical direction. You can see here. Even you can see here, Z2 minus Z1. Okay, when we refer this one, this is ZB, this is ZA. It is 0, ZB minus ZA. The only left is basically this equation. We can use directly. Okay. P2 minus P1. So this one, they are using the 1 and 2. Why don't you use B and A? Replace with B and A. Okay. So I try to, this is the equation, yeah. I try to write it down. Okay, P1, this is the equation. P1 minus, is it P1? P2 minus P1 equal to negative rho AX. Okay, X2 minus X1. Alright. So now it is at the point of B and A. So we can replace PB, okay, minus PA. You must know, yeah, this is the difference in pressure. So I want to calculate the difference in pressure at point A and point B. At this point, after negative rho, okay, this is, this is not rho, this is G. Because you can see here, it is rho, okay, not gamma. So it is rho, it is rho A, okay. So rho of the liquid multiply with the A, okay, multiply with the X, B minus X, A. We must make sure it is tally B minus A, B minus A for the P and X. Alright. So, just substitute. What do you think of PB? PB we need to find, right? We need to discover. How about the PA? What do you think of A? The point A. The PA. What is the value of PA? You can see point A is exposed to what? What do you think the value? And B is not exposed to air. What do you think of PA? Class. Any idea? Please, quick response. What do you think of pressure at point A? The previously, you can see here, pressure at 1 and 2 is 0, right? Because it is exposed to the atmosphere. What do you think of pressure at A? Is it 0 or not 0? And why? Okay. Samuel, Charlie, any idea? What is a PA? Class, are you there?
0.
0. Okay, please respond. It is 0 because at point A, it is exposed to the atmosphere. Okay. Thank you for respond. Okay. Which one? Okay, this one. So we can cancel out PA because it is a 0. So what we left here is PB equal to negative. Okay, density of water is 1000. Multiply with the AX. AX we discovered previously it is. Okay. Where is AX? Yes, this one. 17.66. Okay, 17.66. XB. How to calculate the XB? This is the position, yeah? XB. Where is XB? Okay. This is X. This is X. Okay. What do you think of XB? XB at the position of 0, right? XA is position at 2. You can see the distance 2 meter. So XB is 0, XA is 2. So XB is 0 minus XA is 2. You will get the final answer is 35,300 Pascal. Okay, you can put 35.3 kilopascal as well. Okay, lastly to find the force acting at the bottom, on the bottom of the tank. Okay, so from here we can use the average. Okay, we realize that the pressure distribution is decreasing linearly from PB to PA. Hence, we can use the average pressure over the bottom of the tank. F equal to P B plus PA over 2. Okay, this is the pressure, this is the average pressure. Multiply with the area. Okay, area of the tank from the top view. So PB is 35.3 kilopascal plus the pressure at A is 0, divide with 2, multiply with the area, which is this area, yeah, which is 2 meter by 1 meter, the depth, the width. Okay, 2 meter by 1 meter. So you will get 35, okay, 0.3 kilonewton. Okay, that is the final answer. Okay. I think that's all for today. Please make sure on the 15th of November, you gonna have the test 1. Okay. The test 1 will cover the hydrostatic, the buoyancy force, okay, the Bernoulli equation. Okay, so that things you need to understand lah. It will cover until week 7 chapter. Okay, when you look at here, I try to share with you. Okay. Okay, can you see my CL and CI, course information?
Okay.
Okay, so your target for the question, you're gonna have 3 questions. Okay. Question 1, 5 mark. Question 2, 5 mark. Question 3, 10 mark. Okay. Total 20 mark. Remember your coursework test 1 is 20 mark. Test 2, 20 mark. Your assignment 10 mark. Your programming assignment 10 mark. And final 40 mark. This one. I will share to you later on the programming assignment by using the MATLAB. Okay. So please score the test one. Make sure it is more than 10%. Okay. Please get around 15. Okay, 15%. So the topic cover this one. You must know lah. This fluid property. This is basic, yeah. You must know the basic about the gamma, about the specific gravity. You must know well. Okay. You must know the pressure at rest. How to calculate the pressure inside manometer. This is very important. And then how to calculate the force on plane area. Remember that when the vertical plane submerged in the water, we use the what kind of force? Okay. Do you still remember? The F equal to gamma Hc A. Okay. So that is the force acting at the center of pressure. Okay. Gamma of the liquid. H is the height of the surface to the centroid multiply with the area of the plane, submerged area. And then we learn about the curved body, the curved surface. You must separate into X and Y direction. Okay. In order to calculate the horizontal force using the equation of plane area, F equal to gamma HCA. To calculate the vertical force, it is simply the weight of the body. Okay, the weight of the volume body. Okay. The buoyancy force. Remember, the buoyancy force is basically the force acting vertically upwards at the centroid. So to calculate the buoyancy force it is basically the FB equal to gamma of fluid multiply with displaced volume. Okay, so when you do the free body diagram, when the fluid at rest, the weight of the object equal to the buoyancy force. And today lecture, you learn about stability and linear accelerating container. Remember, to know the stability, you must calculate the GM, the metacentric height. If the metacentric height is negative, it is unstable. So remember the equation for the stability. Metacentric height GM is equal to second moment of area. Okay, divide with the displaced volume minus CG, the centroid of the displaced volume to the center of gravity. From this way, you must differentiate yourself. You must differentiate the question. How to calculate the C? Where is C? C must refer to the centroid of displaced volume. The G refer to the centroid of the body. And then we learn about linearly accelerating container. Alright, we use our equation Z1 minus Z2 or the change in the vertical direction divide with the change in the horizontal direction equal to tangent alpha. That is one equation. Second equation is tangent alpha equal to acceleration in the x direction over with g plus acceleration in z direction. Okay, so that is how you calculate the linear accelerating. Okay, so for the next part, for the next class, I really hope want to cover until week 6 because your tests until this one. Description of fluid motion, classification of fluid flow, and Bernoulli equation. If I'm not cover until this one, you have to study on your own. So it will be difficult lah. So I try my best to cover until the Bernoulli equation, and then you can do your tests. That will be taught by me lah. Okay, is it okay, class? Okay, any question?
No question.
Okay, thank you. So after this, I really hope from your section 11 to section 14, please score very well, okay? I have taught you on week 1 until week 5. Please study on your own. And after this class, I'm going to share you my own tutorial, okay, that cover chapter 2. Please look and understand how I solve the question step by step. Okay, please score well, yeah. I really hope from your effort. Okay, any question before we end our session? Okay, nothing, yeah. All right. I think that's all for today. Okay, thank you very much